So we're already aware that when some reactions take place, they release heat. And what do we call those reactions?
Exothermic?
Exothermic, exactly. Exo, meaning outside. So they release heat, and the outside gets heat from that reaction, and the temperature of the outside goes up. And other reactions actually absorb energy from the surroundings. And what do we call those?
Endothermic?
Endothermic, exactly. Endo means inside. So basically, it's just telling you which direction the heat is going. Exo goes to the outside, endo goes to the inside. And the way to think about this is to just treat it as if heat was either a reactant or a product. Now, is heat the same thing as temperature? What do you think? Is it the same thing or is it something different?
Something different?
It is something different, exactly. Heat is energy. So we've sort of been learning about energy in chemistry, that there's basically two things that when a chemical reaction takes place, there's basically two different ways that energy can be either given off or absorbed. What are the two different things? One is heat. Do you remember what the other one is? So we learned that energy is equal to heat, and heat, remember, is Q. What's the other thing that takes place? What other thing can reflect a change in energy?
W.
W, what's that stand for?
The capacity to do work.
Work, exactly. W for work makes sense. Q for heat, well, you're sort of on your own for that one. Yeah, so that's basically what we're dealing with. The thermochemistry is either heat and or, can be both at the same time, heat and work. Those are the two different things that can take place, representing a change in energy. And so when we're dealing with an exothermic reaction, we're dealing mostly with Q, because Q is heat. Exothermic means releasing heat. So an exothermic reaction would be, let's say, A plus B gives two different products, C and D. So if this was an exothermic reaction, would we consider heat to be a product or a reactant? Which side of the equation should be with the heat?
Product.
It's a product, exactly. Because the heat wasn't there at the beginning of the reaction, and then after the reaction took place, the heat was there. So we can just consider heat to be another product. This reaction makes C, it makes D, and it makes heat. And so when we balance this reaction, remember every reaction needs to be balanced. We need to balance the atoms, and we need to balance the energy as well. And so we consider this, delta H is considered the change in heat, the change in energy at constant pressure when there's no work. And so this would be related to how many moles of A or B are being turned into C and D. So for instance, if this was 1A and 1B makes 2C and 2D, for every mole of A, we release this amount of heat. And so delta H, this capital H, means heat per mole. And so we can use this to calculate the amount of heat from a reaction. Like for instance, if I had 2 moles of A I get twice as much heat. But if you did this reaction and I did this reaction and somebody else did this reaction in like Moscow or something, we would all want to report the same amount of heat. So if you had 1 gram of A and I had 2 grams of A and Yuri had 3 grams of A, we'd all get different amounts of heat released, but the amount of heat per mole would be the same. So that's what the capital H stands for. When you have a delta and a capital H, that means per mole. And so that's something we're going to be calculating today, figuring out heat per mole. And it's generally in per mole of reactant, not moles of product. So let's look at the other side of the coin. Let's look at the same reaction. A plus B gives C and D. Now, if this was an endothermic reaction, would the heat be a reactant or a product?
Reactant.
It would be a reactant this time. That's right, because it basically is one of the things that goes into this reaction that causes products to come out. And so A is necessary for that to happen, B is necessary for that to happen, and heat is necessary for that to happen too. Without the heat, it's not going to happen. And so we consider this a reactant. And so do you know what the difference in the sign, if heat goes into the reaction, if heat is on this side of the reaction, is delta H positive or negative? When heat is a reaction, do I consider that positive or negative for the reaction?
Negative.
Guess again.
Positive.
Positive. And it's positive because it seems a little weird, right? I mean, because with an endothermic reaction, you put your hand on it, it feels cold. That's because the heat is going into the reaction. And so the reaction now has more heat than it did before because it's taking heat from the surroundings and it's going into the reaction. So if the heat is going into the reaction, that means that the change in heat from that reaction is positive. Energy is going into the reaction. So for an endothermic reaction, we say it's positive. And exactly the opposite is true for an exothermic reaction. And again, that seems weird too, right? Because exothermic reaction, like you're burning something, gives off a lot of heat. And so that change in heat feels positive, right? You're warmer because the wood is burning. Well, think about from the opposite side. Ugh, must be somebody coming. Jerome! Think about what's happening from the opposite side. If you are getting heat from that reaction, excuse me for a minute. So, as I was saying, so if you're burning wood in a fireplace, that reaction is releasing a lot of heat. You are getting warm from the energy being released from that reaction. But from the reaction's point of view, that reaction is losing a lot of energy. So remember, energy can't be created or destroyed. It just goes from one place to another place. So that energy that's being lost by the reaction is being gained by you sitting in front, warming your hands by the fire. So for an exothermic reaction, the change in energy is actually negative. So you have to think about which direction the energy is going. If it's going into the reaction, that's positive. If it's coming out of the reaction, that's negative, okay? So let's have a look at some of these questions, and then we'll break up. So this basically is considering, this first question is considering work rather than energy. So we're looking at work. And the question is whether work is being done on the system, whether work is going, we're putting work into the system, or the system is doing work against its surroundings. And so these are all changes in gases. And consider like the classic example is a car engine. So the expansion of exhaust gases, CO2 and water, the expansion of those gases in the cylinder pushes the cylinder out. So the cylinder is basically closed. You shoot in some octane, it explodes, and then you get gases form, CO2 and H2O, and they expand the volume of that cylinder. It is doing work on the surroundings because there's an increase in gas pressure. And so it pushes against the piston, and it does work. So if the amount of gases in a system increases, it's doing work on its surroundings. If the amount of gases decreases, then work is being done on the system. So all of these are a constant pressure. So a constant pressure, either the volume is going to increase or it's going to decrease. So which one of these reactions is either work done on the system, on the surroundings, or no work is being done? So let's look at A. What is that? What are we dealing? What element is this?
Mercury.
It's mercury, right? And mercury, and it's why it's particularly dangerous, is that it converts to gas relatively easily, and that's like mercury vapor. That's something you don't want to breathe. You probably all heard of the Mad Hatter from Alice in Wonderland. Well, at the time that was written, hatters used to felt their material to make hats using mercury, and they would inhale a lot of mercury vapor and go a little swirly. So that's the reason why the character of the Mad Hatter is there. Poor hatters. So in this instance, we've got a liquid going to a gas. Now, is that going to increase the volume or decrease the volume? For each one of these, just think that we've got like a piston. So here's our piston, and then inside we have this reaction going on. So inside this piston, we've got some mercury liquid, and it's being converted into a gas. Now, so the question is, delta V, is this piston going to get pushed up, which would be work being done on the surroundings? Is it being pushed down, which would be work done on the system, or is it not going to move at all?
Work done on the system.
So is the delta V going to be positive or negative? Is it going to go up or down? Which direction? Is it going to be pushed this way or pushed down or pushed up?
Pushed down.
Pushed down, okay. So that would be work done on the system.
Because is it like a liquid takes up more space than a gas? No?
It's exactly the opposite. A gas takes up a lot more space than a liquid. Water vapor takes up a lot more space than a liquid, because one of the defining characteristics of a gas is that there's huge distances between the molecules, right? In a liquid, the molecules are very, very close to each other. They're interacting with each other. In a gas, they're no longer interacting with each other, and they're flying around with huge spaces in between them. So gases take up much more space than liquid. So it's actually the opposite. So the change in volume would be positive. This reaction is doing work because it is producing gas and pushing that piston up. So in that instance, because we now have more gas than we did before, and if you have more gas than you did before, that piston is going to be pushed up, and it is doing work on on the surroundings. So that would be delta W, or change in W would be negative, because that work is being done by the system against the surroundings. Okay, let's try the next one. So this what do we have here? What are these two molecules, O2 and O3? What are those? Gonna make my little piston again.
Is it dioxide and trioxide?
Nope, because they're not an oxide. Oxide is a ion. Remember, so oxide is O-2. That's an oxide ion. These are neutral molecules. So O2, you should know what O2 is.
Oxygen? Oxygen?
It's just oxygen. Yeah, it's elemental oxygen. An elemental oxygen is a molecule. So it is a molecule of oxygen. So that's O2. What's O3? You know what O3 is? That's right, Jean. It's ozone. Ozone. Ozone is another thing you don't want to breathe. Ozone is extremely reactive. One of the reasons why the ozone in the atmosphere is good for us to have is that it absorbs ultraviolet radiation. And when it involves ultraviolet radiation, it goes back to being oxygen. And so it's reactive. It's really good at cleaning things. If you want to basically disinfect something, you can shoot a bunch of ozone into it and it will basically blow up anything that's in there. It'll also pretty much bleach anything in there too, so you want to be careful with it. It's a very active molecule. So on one side of the reaction, we have 3 molecules of oxygen, and on the product side, we've got 2 molecules of ozone. So when that reaction takes place, do we have fewer gas molecules or more gas molecules? So I have 3 moles. We look at it the other way. I have 3 moles of oxygen as reactants. And I got 2 moles of ozone as products. So which is going to take up more space, the reactants or the products?
The reactants?
Will take up more space?
Or would it not be the same?
Well, think about it. 1 mole, what's the volume of 1 mole of gas at standard temperature and pressure? Do you remember?
No.
It's around 22 liters, 22.4. So 1 mole of gas, it doesn't really matter what gas it is, because remember, when we consider the ideal gas laws, we consider that every gas is the same and that they don't interact with each other. And it's not quite true, but it's fairly true. So pretty much every mole of gas takes up around 22 liters. So if I had 3 moles of gas as reactants and 2 moles of gas as products, when the reaction's over, will the products take up more space or less space?
Less.
Less, exactly. Because basically what will happen is if I had 3 moles of gas, I would have 66 liters to start, but then I'd only have 44 liters at the end. And so this piston would be pushed down. And so actually work would be done on the system. So in this instance, work would be positive.
Wait, so all gases have the same volume?
Not exactly, but very, very close. So remember, with the ideal gas laws, we have we sort of consider two big things that aren't quite true. One is that the gas molecules don't interact with each other at all. I mean, they don't really, but there's some small interaction. And the other assumption we make is that individual gas molecules take up zero space, which is obviously, that isn't true. But when you compare it to the amount of empty space between the molecules, it pretty much is true. So because 99.99999% of the volume of a gas is nothing. There's nothing there. There's just molecules moving around with a lot of empty space in between them. So we make that assumption for all gases. So it doesn't really matter what gas it is. They all take up about 22.4 liters for every mole. Not for every gram, for every mole. Because all the molecules, we consider all the molecules to be pretty much the same size in comparison to the space in between them. So that would be work being done to the reaction. Now let's look at the third one. Now we've got a chemical reaction. What's this? What will we call that? What chemical is that? What molecule is that? Ignore that for a minute.
Copper sulfate.
Copper sulfate, right. And when we consider the water, remember we did that experiment earlier where we dried salt and it lost some of its water. Do you remember what we called those?
Precipitation.
Mm-mm. Precipitation is when you have you're creating a solid. In this instance, the solid's already there. It's already a solid. But we basically, remember, we heated it and it lost its water and then the mass of it went down. Do you remember what we called that particular kind of molecule? It's related to water.
Was it like anhydrous or something?
That's right. When is it anhydrous? When it has the water or when it doesn't have the water?
When it has the water.
An means like opposite, right? Or lack of. So something that is anhydrous means it ain't hydrous. It's not hydrous. And hydrous means water, basically. So the an means without water. So if I just had CuSO4, that would be anhydrous copper sulfate. But when it has water, like it does here, there's 5 molecules of water very tightly associated with it because there's a lot of charges here. Copper is +2, sulfate is -2, so there's a lot of charges there, and water is attracted. Water is very polar. It's attracted to charged molecules. So attracted that even in a solid, the water is still there. What do we call it when the water is present?
Hydrous.
Hydrate. Yeah, we just call it hydrate. So this would be copper sulfate hydrate. And I think that even might have been the salt we used, I think. It was some sulfate. It might have been aluminum sulfate hydrate, but it was some kind of hydrate, some sort of sulfate hydrate. So this is the actual reaction that you did. So what we did is that we added heat, right? We put heat in, and when we put heat in, water was given off as a gas, and we were left with the anhydrous copper sulfate. So if I do this in my piston, so I've got my hydrated form in here. I add heat. So which direction is the piston going to go? Is it going to push up and get larger, create a larger volume? Is it not going to change? Or is the piston going to push down?
Say it goes up.
It's going to go up, right? My change in volume is going to be positive because it's creating gas where there was no gas there before. And so I'm creating gas. The volume is going to increase, and this piston is going to move to make it bigger. So is that heat being done? So is that heat being done? Is that work being done on the system, or is that being done on the surroundings? Which direction is the work going into the reaction, or is the work being done by the reaction? Am I putting work into this reaction, or is the reaction doing work against its surroundings?
Work is done on its surroundings.
Right. The reaction is increasing the amount of gas. It's increasing the volume. It's pushing that piston up. So work is being done by the reaction against the surroundings. So that would be minus W, because the reaction is going, the work is coming out of the reaction rather than work being done to the reaction being pushed down. So let's look at this last one. So in this one, I've got hydrogen and I've got fluorine. And what am I making? What do we call that?
Hydrogen fluoride?
Mm-hmm, exactly, hydrogen fluoride. So have a look at that and tell me whether the volume of gas in the reactants is more or less than the volume of gas in the products.
It's the same, right?
Why is it the same? I got two things over here, but I've only got one thing over there, right?
More in
Yeah.
the pro-
What's that?
Is it more in the products?
More in the products, okay. What about who said it was the same? What's the same about them?
You cut off for me. What did you say?
So someone answered it was the same. Which one is the same? What's the same about one side and the other side?
Same amount of moles.
That's right, exactly. Yeah, there would be no change because if I had a mole of hydrogen, H2, and a mole of fluorine, F2, they combined and they make 2 moles of HF. So I had 2 moles of gas at the beginning, and I got 2 moles of gas at the end. So the volumes are the same. So there is no work because nothing happened. I mean, a reaction took place. There may have been heat released, but the volume of my products and the volume of my reactants is the same thing. They're 2 moles. And remember, the volume is directly related to the moles. So they didn't change. Excellent. Okay. So we'll do this one, and then there's one a little bit later we'll do, and then I'll let you go off and do one. So remember what I said about heat being part of the reaction. So this is exothermic. It's a thermite reaction. Has anyone seen, you must have seen Mythbusters at some point. I don't know if you've seen this particular Mythbusters, but they do a thermite reaction, and it is pretty impressive. The amount of heat that is released. So basically what it is oxygen being transferred from iron to aluminum. So that's what's happening. So we have solid aluminum metal, and we add iron oxide. And what happens is that the aluminum is a little more reactive than the iron, and so the oxygen transfers itself from the iron to the aluminum, and it is extremely exothermic. It releases a ton of heat, so much heat that you can weld steel rails together with this reaction. So remember, exothermic means my change is negative. So that means there's heat going out. So the heat would be here as a product. So, and the other thing to remember is that delta H, capital H, delta capital H means kilojoules per mole. That is very, very important. And so if 725 kilojoules of heat, and remember heat is energy, and energy is measured in joules. Temperature is measured in K or C or F. So they're different things. So heat is measured in joules. So if 725 kilojoules of heat are released, does that mean more than 1 mole or less than 1 mole has taken place, has been involved in this reaction?
More than?
So is 725 greater or less than 850?
Because it's negative 150?
Yeah, but see, negative, we don't consider, negative just means which direction the heat is going. We're just looking at the absolute amount. Yeah, that one's a little tricky because yes, you're right. If I said which one's bigger, minus 725 or minus 850, minus 725 in some twisted way is larger because it's closer to being positive, I guess. But in this instance, all we're interested in is which one of these is a larger amount of heat. And in that instance, minus 850 is a larger amount of heat. So that means that less than a mole was involved, okay? So, let's go back. So here's my heat coming out. So the amount of change is 850. So let's say this is a little bit misleading because delta H generally means, per mole. But in this instance, it means for this reaction. So it would be per mole of iron oxide. So for every mole of iron oxide, 850 kilojoules of energy are released. It also means that for every 850 kilojoules of energy, we have 1 mole of Fe2O3. How many moles of iron are formed for every 850 kilojoules of energy?
2.
2, that's right. Because for our balanced reaction, we can basically change this into, what this means is that for every 850 kilojoules, 2 moles of iron. So if I want to see, or I would put it the other way around, 2 moles of iron for every 850 kilojoules. I multiply that by my 725 kilojoules of heat. I get rid of my kilojoules. And how many moles of iron would that be?
1.70588.
So 1.7508?
1.70588.
059. Okay, moles of iron. And then so it's asked what mass of iron is that? So then all I got to do is multiply by, I want grams of iron, and then moles of iron on the bottom. So I just need the molar mass of iron. So what's the the molar mass of iron?
55.845.
5.845. Okay, so how many grams of iron does that give me?
95.265.
0.265 grams of iron. Right, but is that your final answer? I would take points off if that was your final answer.
Are we multiplying by 2?
What?
Are we multiplying it by 2?
We already did that. We already took that into consideration because remember, for every 2 moles of iron, there's 850 kilojoules of energy. So we already considered that.
Big figs?
Yeah, we already considered that.
Is it negative?
Nope, there's no such thing as a negative mass.
Big figs?
There's still a problem with that answer. What's the problem?
The significant figures.
Bingo. Yeah, significant figures. We always have to take into consideration significant figures. And for this, how many significant figures? We have 2, basically we have 2 numbers that go into our significant figure discussion. We have 725 kilojoules of heat are released from this reaction. And we see that the change in energy for this reaction is minus 850. Which one has the fewer significant digits? Or are they the same?
850.
850 has fewer, that's right. How many significant digits does 850 have?
2.
2. That's absolutely right. So if there was a period there, 850 period, it would have 3, but it doesn't. It only has 2. So the proper answer should be 95 grams. So watch for that, like on an exam. Us teachers are very evil. Well, I am anyway. And so we want to, we will throw you by putting in things like 840 dot, and you may think that, what the hell's that dot doing there? That must be a typo. No, it isn't. 840 dot means that it's not 841, then it's not 839. It's exactly 840, meaning 3 significant digits. If it's 840 without the dot, 2 significant digits, because it means it's to the nearest 10. Okay. So the next one is pretty much the same. Oh, heat of formation. Have you guys done heat of formation? Do you know what heat of formation means?
Kinda.
This might be new information as well. Can you explain what it is?
No, definitely not. But we learned it this week.
Okay. What's the reaction of formation? Because basically what we're looking at is what does it mean, reaction of formation? There's a very distinct meaning. Anyone tell me what that means?
Is it for elements in their most stable form?
Right. Yes. That is a big part of it. It is elements in their most stable form. So stable elements making a compound. So we know, or we should know, what's the heat of formation for an element? Like the heat of formation for oxygen. How much energy does it take to form oxygen gas?
$273.15 kelvins.
Nope. Kelvin is not, that's a temperature, that's not a heat. Heat, remember, is in joules. So O2 is the most stable form of oxygen at standard temperature and pressure. So we make an assumption for elements in their most stable form, because we have to have some sort of scale for everything. So what do we set the scale at for elements in their most stable form? How much energy do we say it takes to form them? So
14. 14
14 what?
joules.
So where's that number come from? 14 joules.
That
14
was
joules per mole?
100% a guess.
Where'd the 14, you just pulled 14 out of the air?
Yeah, exactly.
Okay.
Am I close?
No. Well, yeah, fairly close.
13.
Keep going.
Is it like 4 something?
No.
Oh, I don't know.
The answer is 0. So we consider the formation of elements in their most stable form to be 0. It basically takes no energy to form them. And that is our baseline. And then everything from there either is the formation of methanol, for instance, is either exothermic and it takes energy to make it, or it's exothermic and it gives off energy when it's formed. And so the reaction for making any compound, when we have this little F subscript, that means formation, is the formation of this from elements. So which 3 elements, or 4 elements, or 2 elements, or whatever, how many elements are in methanol?
3.
3. And what are they?
Carbon, hydrogen, and oxygen.
Right. Carbon, hydrogen, and oxygen. So next, we look at, so those are the 3 elements involved in making methanol. What are the most stable forms of these 3 elements at standard temperature and pressure, which basically means 1 atmosphere and 25 degrees C. For gases, it's actually 0 degrees C, but whatever. Basically 1 atmosphere and a cool room. What's basically what we're asking, is it a gas, is it a liquid, or is it a solid? And what form is it in? So for carbon, what's the most stable form of carbon at room temperature and 1 atmosphere? Is it a gas, is it a liquid, or is it a solid?
Solid?
It's a solid, right? So it would be C, solid. Now, do we consider, does carbon, is it just by itself? Is it just C, or is it C2, or is it C8, or what is it? Like this form, the most stable form of carbon at room temperature is graphite, like in a pencil. So we just call that C. C for carbon. We do. Yeah, so for the carbon, that's it. It's just C for carbon. That's the most stable form of carbon. It's just C by itself. What about H? Is it a gas, is it a liquid, or is it a solid? So here's our first reactant, solid carbon. What's our next? So the next one is hydrogen. Is it a gas, a liquid, or a solid?
A gas.
It's a gas, big time. So is that the most stable form of hydrogen, just H?
H2.
H2, that's right. H2 is more stable. So H2 gas, that'll be the form of hydrogen, which is the most stable. And so those are our first 2 reactants. Our last reactant is O. So gas, liquid, or solid?
Gas at O2.
Gas. And 2, that's right. So those are our 3 reactants. Those are the 3 atoms that go into making methanol, and they're the most stable form of each of them at STP. So now we got to balance the reaction. Because those three make methanol liquid. Because that's the most stable form of methanol at room temperature is liquid. So is this a balanced reaction?
No.
No. So how are we going to balance it?
You need 2 methanols because there's 2 oxygens.
Okay.
And so now there's 8 hydrogens, so you need 4 hydrogens on the left side.
Okay.
Or 4.
And what about carbon?
They say they can't hear you.
Oh, what about carbon? Is that better?
I don't know. I can hear you, but I don't know if it's...
I'll just turn this up as high as it'll go, try and yell. So what about the carbon? Is the carbon balanced?
No, it needs 2.
Needs 2. Okay. Now this is a bit of a trick question because when we're dealing with the heat of formation for liquid methanol, we're talking about 1 mole of methanol. So that would be the heat of formation for 1 mole of methanol. So actually what we need to do is balance the reaction with this being a 1. So we go back and the carbon becomes 1, the hydrogen becomes 2, and the oxygen becomes a half. Now I know you've sort of been told in the past, like, oh my God, you can't have half of something in a reaction. Well, in this instance, you have to, because delta H, as I've said before, means 1 mole, means per mole. So that's per mole of liquid methanol. So we would need 1 mole of carbon, 2 moles of hydrogen gas, and half a mole of oxygen gas. So you can't do that when we're dealing with molecules, because obviously there's no such thing as half a molecule of oxygen. So that doesn't make sense. But when we're dealing with moles, you absolutely can have half a mole of oxygen. So remember that when we're dealing with delta H, always, 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 especially when the delta HF, always, always, always means per mole formed of whatever it is. In this instance, liquid methanol. So you do what you had to do to put 1 mole of methanol being formed, and everything on the reactant side, you just move it around so that you get the right number of atoms. In this instance, we only need 1 mole of atoms, 1 mole of oxygen atoms, which means half a mole of oxygen molecules. So that would be the reaction. And then so delta H, we don't know what delta H, and this knot here, this thing up here, we call it a knot. Anyone know what that means? That is a very specific meaning. So we have delta H with a little, we call it knot. I mean, it kind of looks like a degree symbol, right? That has a very specific meaning. Anybody know what it is?
I do not.
Okay. Anyone else have a guess? It sort of goes back to what I was saying about at what conditions is carbon a solid and hydrogen a gas and oxygen a gas. What conditions was I talking about earlier? It means basically that this reaction has to take place under specific conditions. What conditions would those be?
STP?
Exactly. Man, you're killing it today. Yes, that means at STP. Because if I did this reaction at 50 degrees C, I get a different number. If I did it at minus 20 degrees C, I get a different number. If I did it at 10 atmospheres of pressure, I get a different number. So this not means that it was done exactly at standard temperature and pressure. And so you can relate it to whoever else does it anywhere in the world. Okay. So this is basically what we've done before. So I'll let you guys work on that one. Same thing with this. Now these last ones are what are called Hess's law. Have you guys discussed Hess's law in class? Oops.
Yeah.
Good. Because Hess's law basically means for this particular reaction, any sort of chemical reaction doesn't mean you went directly from one set of reactants to one set of products. There may be a whole bunch of intermediates in between. So there could be like a whole bunch of different reactions taking place. But at the end of it, we start it with this and we end it with that. But there may have been a lot of other reactions that took place. The thing is, if we add together all the energy of those reactions and add them all together, we'll come out with the same thing. So basically what that means is that it doesn't matter if this is my beginning reaction and this is my product. I can go this way to get there. I can go this way to get there. I can go this way to get there. It doesn't matter how I get there. If I add together all the steps, doesn't matter which path I take, I'll come up to the same place and I'll use exactly the same amount of energy. So basically it means I can predict how much energy a particular reaction is going to take if I know what all the steps are getting there. And so I'll do this with you. So basically what we're trying to do is add up these three reactions to give us this one. And we can do whatever we want to these reactions. We can multiply them, we can divide them, we can flip them around. And when we flip them around, we change the sign of the reaction. So in other words, if a reaction going in this direction is exothermic, if we flip it around and put it in that direction, it becomes endothermic. So let's look at this first reaction. So NO, nitrous oxide, plus ozone gives us nitrogen dioxide plus oxygen. And when that reaction takes place, it releases 198.9 kilojoules for every mole. Now, on the other hand, if I go in the opposite direction, if I say I take oxygen plus nitrogen dioxide and it makes ozone and nitrogen monoxide, that is an endothermic reaction and it takes plus 198.9 kilojoules per mole. So what you're doing when you do these sorts of questions, you're going to look for where are my reactants, where are my products. If my products are on the reactant side, I'm probably going to have to flip that equation around. You know, if my products are on the reactant side, I'm probably going to have to flip that around too. And the other thing you can do is if you have the same thing on both sides of the reaction, let's say I add all my three reactions together, and I find I've got 2 moles of oxygen on one side of the reaction, and I've got 3 moles of oxygen on the product side of the reaction, well, I can just cross that one out, and I'm left with 1 mole of oxygen. It's like net. What do I have net? If I start it with 2 and I end it with 3, then really what's happened is that I ended up with 1, because 2 of them got taken up in the reaction, and then I'm left with 1. Or if I have exactly the same amount of product and reactant on both sides, then that means it really was never there in the first place. It was going into the reaction, coming out of the reaction. If it's the same amount, then really nothing happened to it. 2 moles went in, 2 moles came out. Did you notice any change? No? Well, then we don't have to consider it. That sounds a little confusing. Let's just do one to start out with. So what we want is to end up with that. And we can do whatever we want to get there. So remember, if you flip the reaction around, you change the sign. If you multiply the reaction by 2, you multiply the energy by 2. If you divide the reaction by 2, you divide the energy by 2. So basically, like I said, you treat the energy just like you would a reactant or a product. So where are we going to find nitrogen monoxide? Which reaction is it in, and which side is it in? Is it a product or a reactant? Is it an A, B, or C?
A.
It's an A. And is it the right number of moles?
Mm-hmm.
Okay, so for starters, we'll just start with that. We'll just write that down. So NO, I'm just going to leave out they're all gases, so I'm just going to leave that out. Although, if there's gases and liquids in there, be careful for that, because it takes energy to change something from a liquid to a gas. And if energy is involved in that change, you've got to consider it. So that may come up in other reactions. And so the energy involved in that reaction is minus 198.9. Okay, so O. Now that means elemental oxygen, just O, not O2, not a molecule, just O. So where are we going to find that? Which reaction is that in?
C.
Right, that's in C. And is O a product or a reactant?
Product.
It's a product, right? So we're going to have to flip that around. So that would be, oops, that would be 2O makes O2. Now, is that the right number of molecules? Because that's 2 atoms of oxygen, and we only want 1.
So you would divide by 2?
Probably would. Yeah, I would probably divide that by 2. So I would change this to a 1 and then change that one to a half. So how much energy would be in that particular reaction?
So it would be negative 495 divided by 2.
That's right, exactly. So I flipped it, so it's minus 495 divided by 2. And that is 495 divided by 2. 247.5 minus. Okay, so last, I've got nitrogen dioxide. Where am I going to find that?
A.
That's in A, right. And I've got the right amount of, and that's, so I've got that. So basically, I pretty much have everything I need, but now I have to look at what I've got so far. So I've got nitrogen, I got 1 mole of nitrogen monoxide. That's good. I've got my 1 atom of oxygen. That's good. And I've got my 1 mole of nitrogen dioxide on the right side. That's good. But then I have a problem. My problem is I've got ozone as a reactant, and there's no ozone there's no ozone here. My other problem is that I have a net of half a mole of oxygen gas as a product, and there's no oxygen gas in the reaction either. So I'm probably going to have to use this to deal with that situation. So how am I going to get rid of my ozone?
Would you use B?
I would use B. That's right. I need to use reaction B. Now, reaction B would be considered a classic intermediate reaction, meaning it takes place somewhere along going from products to reactants. But then when you get to the products, it's gone. So we need to use this reaction to get rid of our ozone. So where do we want to put the ozone? Do we want to put it as a product or a reactant?
Product.
Right, we want to put it as a product because the problem we have is that we have ozone as a reactant. Where'd that come from? Right, we can't have it as a reactant when it wasn't there at the beginning. So we need some source of ozone. We need some source of ozone. We need ozone as a product because it had to come from somewhere. So we want ozone as a product. So we flip this one around and we would have 1.5 moles of oxygen make 1 mole of ozone. So what's going to be the energy involved in that reaction?
Positive 142.3.
That's right. So the energy for that one is plus 142.3. Now let's take stock because now we can add everything. And so if something is on both sides in the equal amounts, we can cancel them out. If something's only present as a reactant or only present as a product, we just add them together. So let's add them together. So start with NO is only present as a reactant. So good. So NO. So oxygen atoms, we only have as a reactant. Okay. What about ozone?
We can cancel that out.
Yeah, I've got 1 mole of it as a reactant, and I got 1 mole of it. So here it is as a reactant, and here it is as a product. And there's exactly the same amount on each side, so I can cancel that. What about oxygen? I got O2. Now remember, there's no O2 in the final reaction. So my O2 has to be balanced on both sides. Is it balanced on both sides?
No.
I would argue it is. Have a look at how much oxygen is a product and how much oxygen is a reactant. So here, in this last reaction, I have 1.5 moles of oxygen as a reactant. How many moles of oxygen are products in the other two?
1.5 moles.
That's right. I have 1 mole here as a product, and I have 0.5 mole here as a product. So I have 1.5 moles of oxygen as products. I got 1.5 moles of oxygen as reactants. So they all cancel. So then the only thing left as a product, everything else is canceled. The only thing left as a product is NO2. And that is our final, that's the one we were looking for. So after we add up everything here, I have 1 mole of NO, I have 1 mole of O, and I have 1 mole of NO2 on the other side. So I'm good to go. So now all I need to do is just add up all my energies. So if you remember, we didn't do anything to reaction A, so the energy stayed the same. We flipped, we just divided. Wait a minute, no, we flipped reaction B around, and we divided it. Did we divide it by anything? Oh, I'm sorry. No. We took reaction C and divided it by 2. That's this one. This is reaction C, and we divided that by 2. So it went from, and we flipped it around. We did a lot to that one. So we turned this into a negative, and we divided it by 2. So that's minus 247.5. That's where that came from. And then the last one was just reaction B that we flipped around. So that went from minus 142.3 to plus 142.3. So we add, finally, minus 198, minus 247.5, and plus 142.3. So what's our final answer?
Negative 304.1.
Negative 304.1 kilojoules.
So you just would add those together?
Yep. Yeah, that's all you do. Because that's what Hess's law tells you, is that it doesn't matter what reactions you need. If those reactions all take place, and these are your final products, and these are your final reactants that went into it, you just add all the reactions together. And so whatever energy, positive or negative, whatever takes place, you just add them all together. So if I have more exothermic reactions than endothermic reactions, my final reaction is going to be exothermic. If I have more endothermic reactions than exothermic reactions, my final reaction is going to be endothermic. It's just, where does the energy go? It's going in and it's coming out. And you just add it all together at the end. Do you want to do one more? We'll do the last one together as well. I'll let you guys take more of a. So I do find these fun, which is, I know it's kind of sick, but all right, this one might be a little trickier. So, what kind of reaction is this? It goes back to just what we've been talking about in an earlier question.
Combustion?
Yeah, it's a combustion reaction. Actually, I was going to say it would be delta H formation, but I can't say that. How come? There's something wrong with it. This side is fine. Those are the two most stable forms of hydrogen and oxygen at STP. What about the product?
It's not a liquid.
It's not a liquid. That's right. So this isn't delta H formation. It's a combustion reaction, right? So delta H. So we need to figure out what's delta H for when you take 3 moles of hydrogen and react it with a mole of ozone and get water. So we'll start the way we normally do with these, is where do we find our hydrogen? Which reaction?
The first one.
And is that the right amount of hydrogen?
No, so you would multiply everything by 3/2, right?
Yep, exactly. So multiply everything by 3/2. So that would give me 3 hydrogens plus 1.5, or 3/2, whatever, moles of oxygen make 3/2. Oh, 3/2, no, 3, duh. 3 moles of water. So what would be the energy involved? And they're all gases, so I will leave off the states of matter. They're all, so how much energy would be involved in that reaction?
Negative 725.4.
Right, that takes more, 725, not with a period. 725.4?
Mhm.
Okay, kilojoules. And next, we need ozone. So where are we going to find ozone?
B.
That's in B. And this is the right amount of ozone.
No.
No. So what are we going to have to do to, is ozone in the right place? Is it, we need it as a reactant.
No.
And
So you divide by 2 and then turn it around.
Right. So we need to flip it around. So we need to flip it and divide by 2. So in other words, instead of making 2 moles of ozone, I want to have 1 mole of ozone on the reactant side and have it make 3/2 moles of oxygen as a product. So what would be the delta H for that reaction?
142.3. Negative.
So it goes from being positive to negative, and we divide it by 2. So what's the?
Negative 142.3.
142.3. Okay, so now we sort of take stock and we add these things together. So I've got, so net at the end, I've got 3 hydrogen molecules. That's good. I've got 3 moles of water. That's good. I got 1 mole of ozone. That's good. And what about the oxygen?
It cancels out.
O2. What happens to it?
It cancels out.
Right, because I've got 3/2 moles as a product, as a reactant, and I got 3/2 molecules as a product. So that goes away. So these are the only 3 things I have left. 3H2, 1O3, 3 waters, which is exactly what we wanted. So now we just add together these 2. And that will be our final answer. And you can always check these too. Excuse me. If you're working on these at home, you can always check them, because you can just go to Google and say, 3H2 plus O3 makes 3H2O energy, and it will tell you. They'll give you the delta H. And so it should be the same answer that you come up with using Hess's law. So that's our final answer.
Negative 867.7.
167.7 kilojoules. Yep. There you go. And so, yeah, so someone want to check that? Someone want to Google that and see if we got the right answer? You just do 3H2 plus O3 equals 3H2O. And it should tell you what the energy is. Did we get it right?
Yeah, this is negative 867.7.
Bingo. So we got it right. Yeah, so that's the nice thing about these questions. You can always check your answer. Or if you're just completely flummoxed and you don't know how to get there, at least you can see what the answer should be, but you always have to show your work. So like, on a test or something, if you just gave the answer, you wouldn't get credit for it, because you need to show how you got there. You would need to show your calculations. Always, always, always. All right, so there's a couple we didn't do. You guys just want to go off and do them, or shall we just hang out and do them together?
Do them together.
What was that?
Do them together.
Sure. Okay. I'm going to let you guys take the. Okay. So let's start with, so this one. So reference pages, we're going to need heat of formation for some of these. So for this, you can add together heats of formation to figure out what the final heat of formation of a product is. So we would need to figure out how much heat goes into making each one of these things. So we need to heat released or consumed when solid silica reacts with this below. So have you done the, have you looked at these sort of reactions, looking at heats of formation? What do you do with heats of formation? Can you add them together? Do you subtract them? Do you know what to do with them for this sort of question? Or you have no idea what we're doing with heats of formation here?
Yeah, that one.
Fair enough. So we can figure out what the heat of this overall reaction is by looking at the heats of formation of each one of these things. So we would take the heat of formation of silica dioxide and the heat of formation of HCl and the heat of formation of silicon tetrachloride and the heat of formation of water. Now, the heat of formation is the amount of heat released or consumed when you form a molecule, right? Not when you blow it up. So when you form it. So which two of these molecules are being formed? In this reaction, we have two molecules being formed. Which two are they?
The products?
The products, right. So we are literally forming these two. So we would add together the heat of formation of our silicon tetrachloride and the heat of formation of water.
But isn't the water in a gas form?
Yes, so exactly right. So we would need to look up the heat of formation of water in a gas form. That's absolutely right. Because the heat of formation of water liquid is going to be different. It takes less energy to make water liquid than it does to make water gas, because you need to take water, you need to add more energy to get it to go from a liquid to a gas. So the heat of formation of water gas would be a little bit higher. But, so we'll do that, we'll add those heats of formation together because we're actually forming them. What about these other two though? What do we do with the heats of formation of the silicon dioxide and the HCl? Because we're not actually forming those, are we? What are we doing with those molecules? Are we forming them?
You're like taking them apart?
Exactly. We're doing the opposite of those. So heat released during the heat of formation is literally, that's the heat either released or consumed when you make the bonds that form our products. We're actually making those bonds that form products. Well, what happens to the poor reactants? Those bonds are broken. That's the opposite of forming bonds, right? So what do you think we're going to do with the heats of formation for our reactants?
Making them negative?
Exactly. Yeah, because we're doing exactly the opposite. So if it takes heat to make a product, it actually releases heat when you go the opposite direction. Just like with Hess's law, if I'm going in one direction, if it's positive going to the right, well, it's going to be negative when I go to the left. So whatever the heat of formation of silicon dioxide and HCl is, I'm going to subtract those because they're opposite. So I'm going to have minus HF SiO4 and minus HF HCl plus these two. So this is going to be plus for the products and negative minus for the reactants. What else do we have to do? Considering this is a balanced reaction, what does, oops, so delta HF for HCl gas. Remember what I said, what does delta capital H mean? For how much? How much HCl am I forming when I say capital HF?
1 mole.
1, that's right. That means per 1 mole. 1. So if I'm taking apart 4 moles of HCl, what do I have to do to the delta HF of HCl?
Multiply it by 4.
Bingo, man. Yes, yes, indeed. Arissa, you're large and in charge. So yeah, it means I got to multiply that by 4. So not only am I subtracting it, I'm multiplying it by 4. Same is true with my water. Since we're forming 2 moles of water, that means whatever heat is involved with forming 1 mole of water, I need to multiply that by 2. So when you get right down to it, what that means at the end, that the overall reaction, the heat involved in this overall reaction is I subtract the heat of formation of 1 mole of silicon dioxide. I subtract the heat of formation of 4 moles of HCl. Oops, put that in the wrong place. Here's where I want to put my 4. I add the heat of formation of 1 mole of silicon dioxide, silicon tritetrachloride, and I add 2 moles the heat of formation of water, gas. So then you just look these up. And she says they're provided on a reference page, and I think there's a hyperlink to that. I don't know if the hyperlink works in a PDF, but that's how you would do that problem. So that would be per mole of silicon dioxide. But we're not done, right? Because we didn't, so can we figure out what these numbers are first? So can we look up the heat of formation for silicon tetrachloride gas? Oh, we have that one. So that we have this one. So minus 657. What about water? Gaseous water. Do we know what that one is?
The link in the thingy doesn't work. Like
Doesn't
the
work?
reference page.
All right, so you're gonna have to Google them. Right, so you Google those then. Solid silicon dioxide, HCl gas, and water gas. Then, when you have that number, let's say, let's say the number is, 560.8 kilojoules. Let's just say that that's our final answer. That isn't the final answer though. Why isn't it?
Because you have 22.5 grams of solid silica.
That's right. This is based on 1 mole of silicon dioxide. So 1 mole of silicon dioxide, 4 moles of HCl, 1 mole of silicon tetrachloride, and 2 moles of water. Well, we don't have a mole of silicon dioxide. At least I don't think so. We only have 22.5. So we would take this number, which is per mole, and multiply that by 22.5 grams, and then figure out how many moles that is. So we need to convert 22.5 grams to moles, and then multiply that by minus 560. That would give us our final answer. So on a test or something, you wouldn't have to look up any of these. She would give you the heats of formation of all of these things. The thing to remember, the sort of the take-home thing to remember, is that for all these reactions, if I am forming a product, then I use the heat of formation. If it's a reactant, remember, I'm doing the exact opposite. And so I'm breaking those bonds. So whatever the heat of formation is, it's negative that, because I'm doing the exact opposite. I'm not forming the bonds that go into that molecule. I'm breaking them apart. So it's exactly the opposite. So for silicon tetrachloride here, when I make that, when I make those bonds, I get out 657 kilojoules for every mole. If I want to break those bonds, I got to add 657 kilojoules per mole to break those. And that makes sense. Like if energy is released when you make something, then you've got to add energy to go the opposite direction.
So if the heat of formation is already negative, but it's on the reactant side, then you would turn it positive, right?
Yep.
Okay.
Yep. Whatever it is, if it's positive or negative, you go the opposite. So, and then remember to consider the number of moles, because heat of formation is always, always, always per mole. So if you need 4 moles of that thing, then you've got to multiply by 4. Or if it's, if you only need half a mole, then you got to, multiply by 1/2. With all of these questions, just consider energy as you would a reactant or a product. If it's going in or if it's coming out, that changes the sign. And remember, it's per mole. So you got to multiply it. Just like you balance moles on each side, you have to balance the energies on each side. And they're always given per moles. Let's do the last one. I think there's only one left, right? Ooh, on roasting. Roast. All right, so always check. There's another thing to be, that I'm an evil person like me would give you a reaction and not balance it, just to see if you're paying attention. So whenever you're given a reaction like this, make sure it's balanced. Okay, so have a look. Is this a balanced reaction?
Yes.
Yeah, so I got 2 zincs, 2 zincs. I've got 2, 4 oxygens, 6. Yeah, so that works. So it's a balanced reaction. Oh, yeah, 2 sulfurs, 2 sulfurs. Okay. What is a little confusing is this kilojoules per mole. That is a little confusing. So I would assume that with this reaction, you get twice as much heat because generally delta H reaction would be for every mole of reactant. And so I think that this delta H for this reaction should be twice as much. That part's confusing to me. So yeah, I didn't write this one. I would just have delta H. I would leave that off, but so that one's a little tricky. So we'll just have to assume that delta H for this reaction is minus 879. Okay. Interesting. I'll figure out what she means by that, and then I'll give you an announcement. But anyway, what do we do with what's the question asking? It's asking how much heat is evolved. So heat evolved means it's exothermic, and this is an exothermic reaction because it's negative, per gram of zinc sulfide. So what's the very first thing we're going to need to do?
So are they asking for initial heat?
So basically, if I reacted 1 gram of zinc sulfide with oxygen, how much heat would be given off? That's the question.
But why do they give you that? So, because like, what's the delta H? Isn't that what that is?
Delta H is the amount of heat given off for this reaction in moles.
So they're just asking for it in grams?
Yes.
Oh.
So what's the very first thing we need to do?
Find the molar mass of ZnS.
Yeah, zinc sulfide. Yes, exactly right. So we need to know how many moles that is because we're always given delta H in moles, right? So 1 gram of zinc sulfide is how many moles? I don't know. So how do we figure that out? Well, grams at the bottom, moles on top. So how much is 1 mole of zinc sulfide? What's the mass of that?
97.474.
474. Right. So how many moles is that?
Zero 0.010259.
Okay. So that's how many moles. So we know that in this reaction, it releases minus 879 kilojoules for every mole. So then all I got to do is multiply that by 0.01026 moles. Moles go away. And so it's minus 879 times 0.01026. So how much heat is that?
Negative 9.01779.
Kilojoules. And I think that's it. But what's confusing about this is that I don't know whether it's 879 kilojoules for every 2 moles of zinc sulfide or whether that part's confusing. So I will, like I said, I will look in and see exactly what that means. Because that's a confusing way that question is given. Because if it is per mole, then you're done. Moles, you got moles here, you got moles here. So I will find that out for you. The only other thing to consider is how many significant digits should we have?
3.
You sure? That part's confusing too.
1.
Well, that's just it. I don't know because per gram, because if she said, if I had for 1 gram, how much that would be 1 significant digit. Per gram could mean 1.0, 1.00. I'm not sure. So again, this is a very poorly worded question. So I would probably default to the number of significant digits given in the heat and then round that to 900 minus 902 kilojoules per gram. Yeah, that's a That's a bad question. I apologize. That's a weird question. So there's a lot to look into. I will get back to you with exactly what the correct answer for that is. But the way it is written right here, that is the answer. Minus 9.02 kilojoules per gram. So remember, if you're asked for joules, because most of these are in kilojoules because you're dealing with moles of material, which is a lot of material. If you need to convert to joules, remember that a kilojoule is 1,000 joules. So you may get, so this would be 9,020 joules negative. Just in case the question is in joules. So I think that's all of them. Any other? Oh, John, what was that? Minus 241.8. What was that from? Sorry, I didn't see that in the chat. Oh, formation of H2O gas. Thank you. So I think that's all the questions because we're not going to do the calorimetry till next week. So are there any, now that I've got everyone completely confused, are there any other questions? Do you want to review any of these with a few minutes we have left? Or do you have any other questions about them? So I think we're going to be talking more about thermo in the next week and then more about calorimetry, particularly in the lab. We'll talk more about calorimetry when we do the lab next week.
Professor?
Yeah.
Can I speak to you when everyone is gone?
Sure, of course.
Thank you.
No problem. So any other questions? No? So you're sure about these, right? You got them all nailed?
No, I think we're all just confused personally.
Yeah, I apologize. But you know, we'll go slowly. Yeah, next week we'll be doing more of these and calorimetry questions too. So I think you'll have a better idea because I think this is just brand new for most everybody. And so, yeah, this just the things to take away are you treat energy just like you do reactants or products. So if it's coming, you have to balance it on both sides. So, and it's always given per mole, or it's just given an amount of heat, and then you have to determine, like if this was just minus 879, then for this reaction, then you would know for every 2 moles of zinc sulfide, that amount of heat was given off. So then for every 1 mole would be half that. So you just treat it just like you would a product or reactant. And then that's how Hess's law works. If it goes in, it's got to come out. We balance everything. We add everything on one side, everything on the other side. If we have the same thing on both sides, we cancel them out. If we have more on one side than the other, one side cancels out and we have leftover on the other. So yeah, look over these again. There's practice problems to work on as well. And I think she's probably given you some other problems, some practice problems as well, right?
Oh yeah, like the problem sets.
Yeah, have a look at those, and then so next week we'll be able to get into this a little bit more. And if you have any questions, as usual, get in touch with me. We can either have a Zoom and do them together, or a group meeting. I keep saying that. Been in research for so long. Office hours next Wednesday. We can work on some of these then as well. All right.
Should all questions about the research paper be directed towards Professor Schubert?
No, you can ask me about that. She's going to be the one grading it, but you can ask me about it.
Okay.
But yeah, she'd probably give you because she knows better what she's looking for. So yeah, I would probably direct most questions to her, but I can help you out with them.